everyone, welcome to Learning at 11th Hour. Today we are going to discuss a few numericals on two-port networks. I've observed that at least there's one problem related to two-port networks that's asked every year in the GATE examination. So I've picked up about three problems to be discussed in this video. Let's get into the video. So this is the first problem wherein we've been asked to compute the admittance parameters for this given network. They have given us four options to choose from. But that's okay. Let's try to compute it in the um, normal way, right? So to begin with, we know that we need to compute the admittance parameters, which means y parameters, and therefore we can write out the equations as follows, right? So this is going to be I1, I2 is equal to the admittance matrix y11, y12, y21, y22, v1, v2. Now, in order to compute this, we are actually going to compute the currents I1 and I2 in terms of the admittance and the voltages of the two ports V1 and V2. So, if we see, these are the two ports. This is these are the two nodes, and I'll call this as node 1. I'll call this as node 2, and therefore the voltage here is also V2, which is true because it's with reference to the negative terminal, and the voltage here is V1. Now, we can consider the current directions in this manner. So this is I1, which is already there. We can consider that there is a current coming out from this node into the 1 ohm resistance here and here. And there is a 3V2, a dependent current coming into the node. So if we write the KCL equation for node 1, so writing KCL at node 1. So we basically get it as plus I1 entering the node plus 3V2 entering the node minus V1 by 1 for this particular current, and minus, because this is going out from V1, I mean node 1, V1 minus V2 by 1. All this put together should be equal to 0. So if I uh, rearrange this, making I1 the subject of my equation, I will get I1 is actually equal to 2v1 minus 4v2, and I'll call this my first equation. Let me apply the KCL at node 2, and on doing that, what do I get? So here we see that I2 is entering the second node, and I can assume that this is a going out of this node, and I can also consider another current entering into 1 ohm resistance. So we can write the equation as plus I2 entering node 2 minus V2 by 1 for this particular current, and for this one you have minus V2 minus V1 by 1 put together is 0. That basically is I2 minus V2 minus V2 plus V1 is 0, and therefore I2 becomes equal to minus V1 plus 2 times of V2. This becomes the second equation. And from the two equations over here, we observe that the coefficients of V1 and V2 for the first equation is Y11 being 2 ohms. Sorry, in this case, this is 2 more because these are Y parameters. And Y12 is equal to minus 4, and Y21 is equal to minus 1, and y22 becomes equal to 2. Moving on to the next numerical. In this, we've been given the impedance matrix, and we have to compute the value of ZL for which maximum power can be transferred to it. Now, according to the maximum power transfer theorem, we know that maximum power will reach the load ZL, provided ZL is made equal to ZTH, which is the Thevenin's impedance. So if I'm able to compute the Thevenin's impedance of this particular network over here, in that case, ZL should be equal to that, and that is when maximum power is going to reach it. So we need to compute ZTH, which means we need to know VOC, the open circuit voltage, which is nothing but V2 when this is in open circuit condition, and ISC, which is I2 when this is short circuited. So this is what we need to compute. Now, given the impedance matrix, we can write out the equation. V1 is equal to 40 I1 plus 60 I2, and V2 is equal to 60 I1 plus 120 I2. So having known this, we can say that the open circuit voltage has to be computed, and for that, it means when it is open circuited, I2 is going to be equal to 0. So the open circuit condition, under open circuit, I2 becomes equal to 0. So when I put I2 0 in both of these equations, what do I get? So here we get V1 is equal to 40 I1. I2 becomes 0, and V2 is equal to 60 I1. Now, what is V1? V1 is nothing but, let me write it out over here. So I can apply KVL in the small loop to compute V1. So from this, I can get minus 120 plus 10 I1 plus V1 is equal to 0. Therefore, I can say that V1 is equal to 120 minus 10 I1. So having known V1, I can replace it over here. So I'm going to rewrite this as 120 minus 10 I1 is equal to 40 I1. Therefore, I can say 120 is going to be equal to 50 I1, or I1 is going to be equal to 12 by 5 amps. If I am able to replace this over here, I'll be able to compute V2, and V2 is nothing but VOC in this case, because I have considered I2 is 0, that is open circuit condition. So the voltage across the two terminals, which is V2, will be VOC. Therefore, let me just replace I1 over here to obtain it. So we would basically obtain it as 60 into 12 by 5, which is 144 volts. Now that we've got VOC, we need to compute ISC. Now to obtain ISC, we are going to consider short circuit. So short circuit condition here basically means that V2 is going to be 0. So if I'm able to place this V2 as 0 in this particular equation, what do I get? I will end up with V2 being equal to 0 is 60 I1 plus 120 I2. So simplifying this, we get 60 I1 is minus 120 I2, or I1 is equal to minus 2 times of I2. Now let me try to simplify this part, where I'm just going to replace V1 with 120 minus 10 I1 in the first equation. So 120 minus 10 I1, and here I'm going to be left out with 40 I1 plus 60 I2. Now I get it as 120 is equal to 50 I1 plus 60 I2. Here I can replace I1 with minus 2 I2, because after all I need to compute I2 in this case, which will actually act as the short circuit current, right? So I'm going to replace I1 with in terms of I2 rather. So I'll get it as minus 100 I2 plus 60 I2 is 120, and that turns out to be minus 40 I2. So when I simplify this, I get minus 3 amps is my short circuit current. Now, in order to compute ZTH, which is the final ZL which I need, I just need to divide VOC by ISC, where VOC was 144 and ISC is 3. So when I divide this is going to be 48 ohms. That's the answer for this particular problem. On similar note, we can actually compute the solution for the next numerical. So here if we see, we've been given this problem. This was asked in gate 22, 2022, and we've been given a lot of information here. So we've been given this network, and they say that this resistance R is being varied, and we need to when we vary this resistance R, this is the kind of plot that we get. They ask us to compute what would the current I2 be if I'm going to replace this resistance R with this kind of a terminal, that is a 1 kilo ohm with a 10 volts connected to it. So if we think about it, this is also, you can compute this with the Thevenin's concept. So if we are able to boil down this network into a Thevenin's, in that case, we'll be getting the VTH here, the RTH over here. This is my terminal A and B. To this, I would be connecting this particular uh, network that's been given. So 1 kilo ohm plus 10 volts. So this is what my final thing would look like. They are asking us to compute I2. That would be I2. So for that, we need to know VTH and RTH. This is pretty similar to the previous problem. So again, we need to obtain VOC, open circuit voltage, and ISC. That's our target. So VOC will be obtained when I2 is equal to 0. ISC can be obtained when V2 is equal to 0. Now let's look at this graph. From this, we can actually obtain VOC very easily, because for I2 equal to 0, V2 is actually 5 volts. So this coordinate is 0 comma 5. So here, of course, they are considering minus I2 over here, which means they are considering this direction. So that is 0. For that, we have V2 as 5 volts. So our VOC basically is 5 volts. We need to compute the short circuit current next, which is I2 when V2 is equal to 0. So this is what we need to compute next. So if we look at this plot, right, I have extended this plot over here, and at this point, my curve meets the x-axis. So this is when my y is equal to 0. Y is nothing but V2. So for V2 equal to 0, what is this value of current that is there? If we are able to compute this, we get our short circuit current. So if we are able to obtain the equation of this particular line, y is equal to mx plus c, then we can replace y with 0 and find the value of x, knowing the intercepts value and the slopes value. So to find m, y2 minus y1 by x2 minus x1 can be used. Here y2 is 5, y1 is 4, x2 is 0, x1 is 4 milliamps. So I can write this as 5 minus 4 by 0 minus 4 into 10 power minus 3. So that is 1 by 4 into 10 to the power 3, and there is a minus sign here. So that's 1000 divided by 4. So this is 250. This is my slope. In order to find the value of C for the equation of this line, So let's try to find that out. Y is equal to minus 250x plus c. So I know this coordinate, right? This is 0 comma 5. So x is 0 and y is 5. So when I replace it, I get 5 is equal to minus 250 into 0 plus c. Rather, c is equal to 5. So the equation for this line is y is equal to minus 250x plus 5. Now we need to compute this particular coordinate over here. So we know the y coordinate here, which is 0. We need to find out x. So when I replace this as 0, I get 250x is equal to 5. Therefore, x is equal to 5 by 250, which is 1 by 50. So the value of I2, therefore, can I write it as 20 milliamps, right? Now, now that I know the value of I2, which is ISC in this case, because I've considered V2 to be 0 here, and I also know the value of the open circuit voltage, which is 5 volts, now I can compute RTH. So RTH now becomes 5 by 20 milliamps. So that is 5 into 1000 by 20. So which is 250. So RTH over here is 250 ohms. Having said that, we can now replace the values of VTH and RTH over here and then find out I2. So I'm going to redraw the circuit here and I'll get it as this is plus minus 5 volts, RTH being 250. I have a 1 kilo ohm over here and a 10 volts over here. So if I need to compute the current over here, I can simply write it as 10 minus 5 divided by 1250 because it's the same current which is flowing through it. That is going to be my I2, which is 5 divided by 1250. So that turns out to be 4 milliamps. So in this manner, we see that even though this problem is a two-port network problem, the concept of Thevenin's, also comes into this picture, which helps us to resolve the different parameters of this network under different scenarios. So that's all with today's video. I hope this video was useful to you all. Please do subscribe to this channel for more such videos on circuit theory. Thanks for watching.